Hello everyone. Today we're gonna have our last 3 data structures series. Part 5 out of 5. We're gonna learn to extract useful information out of tree using recursion. These methods are popularly known as PreOrder, InOrder, and PostOrder traversals. We're also gonna explore some more recursions to extract useful information out of the tree, which are less popular but yet still very useful. We absolutely need the knowledge of function call stack and recursion, which is presented in part 4, so please make sure to check it out if you haven't done so. This tutorial is a part of the data structures and algorithms class. First, how do we extract useful information out of the tree with recursion? At this point, you should have a pretty good understanding about function call stack and recursion. We have learned that recursion can be used to process data point after data point until there's no data point left. Now we're gonna apply this knowledge to extract useful information out of the tree. We already done a lot of heavy lifting when learning about function call stack and recursion in part 4. So for today's tutorial, it should be very straightforward to apply these knowledge to extract useful information out of the tree. A quick reminder for our tree problems. When we at humans solving tree problems, what we do is we look at the data of the whole tree at a time and we freely select nodes as asked by the problem. And the equivalent computer execution is, for looking over the data at the same time, the computer will look at one node at a time. And we'll apply the logic to only current node, and then it's gonna use loop or recursion to visit all of the remaining nodes. To select the order of node visitation, the computer execution is it's gonna use stack or queue, or change the position of the recursive call to control the order of node selection. And this is what we're gonna learn today. We're gonna learn how to use recursion to visit all of the nodes, and we're gonna learn how to change the position of the recursive call to control the order of node visitation. These methods usually known as tree traversal. We have 3 popular official names for tree traversal: PreOrder, InOrder, and PostOrder traversal. Traverse means walk. Tree traversal means walking the tree. Walking the tree simply means we go from one node to another. In short, tree traversal is just a fancy name for a tree node visitation in a particular order. Next, we're gonna learn about PreOrder traversal. The usefulness of this particular order of node visitation is whenever it gives values to your application. That means when we use PreOrder traversal, we already know this is the order of node visitation: 1, 2, 3, and 4. So if we find it useful, we can use this for our application. The order of node visitation is already determined. Okay, let's look at the code. It's a really simple recursion function. It's only had 3 lines of code. The first line, we process the current node. Here we only save the node data to the result array. In real-life application, we can do anything with the node data that we want. The second line is a recursive call. This syntax is a shorthand for if condition. If the node have the left child, we call the recursion function with the new data is the left child. The third line is the same with the right child. And that's it. With only 3 lines, we can process the whole tree, no matter how big or small it is. Now let's get to the name. How to remember this name and connect it to the code. It's fairly quite simple. When we talk about PreOrder, order is left then right. Pre means before. So when we say PreOrder, that means we process the node before the left and right traversal. So this is pre and this is order. So PreOrder name itself already say how the code looks like. So that's the name and the code. Then how do we get this result? If we do a PreOrder traversal for this tree, we're gonna have a result of 6, 4, 1, 5, 8, and 10. That's what we have here. The correct way to get this result is we're gonna need to draw out a call stack of this function and run it for the whole tree, which we already learned how to do so in the previous tutorial. Today I'm gonna show you another trick to do it faster without a call stack. But you absolutely need to know how to do it with a call stack, because that's the real source of truth. What I am about to show you is just a trick. So the trick is you draw out a tree and you put PreOrder right next to each node. Now we're gonna process node after node. First, we start with root node. We process first. That means we put 6 into the result array. Then we do the left traversal, meaning we're gonna go to the left child of 6. Now we add 4. Then we process 4. And we put 4 into the result array. Then we do the left traversal from 4. That means we're gonna go left of 4. We go left of 4 and we see 1. Then we're gonna process 1. We put 1 into the result array. Then we do the left traversal of 1, but 1 doesn't have a left child. so the recursive call will not run. Then we do the right traversal of 1, and 1 doesn't have a right child, so the recursive function will not run. And then we finish all the operation of node 1. That means we're gonna go back to node 4. We at 4, and now we're gonna do a recursive call for a right child at 4. So we go right, and we see 5. And we're gonna continue our order of node processing. We put 5 into a result array. We traverse left and right of 5. Then we finish 5. And we go back to 4. And we finish 4. We go back to 6. Now we're gonna do the right traversal of 6. We go right and we see 8. So we're gonna put 8 into the result array. We traverse left. We traverse right. We see 10. We put 10 into the result array. There's no traversal for the left and right of 10. So we finish 10, and then we finish our tree. The traversal order is gonna look like this. 6 to 4 to 1, 5, 8, and 10. Remember, if your tree is bigger or have more nodes on left and right, the arrows will go deeper to reach more nodes in their directions. For implementation, this is our PreOrder traversal. In our binary search tree data structure, in PreOrder method, we simply check if a root node exists. Then we initialize the result array. We call our recursion function, and then we return the result array. And this is our recursion function for PreOrder traversal. If we run that with our tree, it's gonna give us 6, 4, 1, 5, 8, 10. Next, we're gonna learn about InOrder traversal. This particular node visitation order, we're gonna print out the min value from the max value in our binary search tree. Let's have a look at the code of InOrder traversal. You can see that it looks exactly the same with PreOrder traversal. The difference is the step of processing the node is now between the left and right recursive calls. And just by changing the position of the recursive calls, like we see here, we have a totally different order of node visitation. It's gonna go like this: 1, 4, 5, 6, 8, 10. How can it happen like this? Just one change of the position of the recursive call. The node visitation order has changed. Well, it's really simple. It's because of the nature of our function called stack. If you draw out the call stack, you can see that the nodes are going to be visited and processed in this order. Now let's look at the name, InOrder traversal. Again, order means left and right. In means between. So for InOrder, we put the processing step between left and right. So InOrder is the way how the code looks like. Now let's quickly run our trick to see how we're able to get this result. First, we start at the root node, then we go left. Then we see 4, and then we go left. Then we see 1, and we go left. There's nothing there, and then we process. We put 1 into the result array. Then we go right. There's nothing in the right of 1, and we finish 1. We go back to 4, and we process 4. So we put 4 into the result array. Then we go right. We go right, and we see 5. Then we go left of 5. There's nothing, and then we process 5. We put 5 into the result array. Then we go right of 5. And there's nothing. Then we finish 5. And then we finish 4. We return to 6. Then we process 6. We put 6 in the result array. Then we go right of 6. Then we see 8. We go left of 8. There's nothing. Then we process 8. We put 8 into the result array. Then we go right of 8. Then we see 10. We go left of 10. There's nothing. Then we process 10. We put 10 into the result array. Then we go right of 10. And there's nothing. So we finished. And then we have our result of 1, 4, 5, 6, 8, 10. And that's the order of node visitation with InOrder traversal. 1, 2. And with the result, you can see that InOrder traversal, you're gonna visit everything from minimum value to max value. Now let's have a look at the code. InOrder traversal looks exactly like the same PreOrder traversal, with just one single difference, which is the position of the left recursive call is now before the processing step. And if we run InOrder traversal, it's gonna give us 1, 4, 5, 6, 8, 10. Next, let's have a look at PostOrder traversal. Again, if we look at the PostOrder recursion function, it looks exactly like the same with the two previous traversals. The only difference is the position of the left and right recursive calls is now before the processing step. And the name PostOrder already shows how the code looks like. Again, order is left and right, post is after. So we process the node after the left and right recursive calls. if we run PostOrder traversal for this tree, our result is gonna be 154, 10A6. With our trick to get the result, we have our tree and our PostOrder right next to each node. And then we're gonna start from the root node. We start at 6, and then we go left, and we see 4, and then we go left, and then we see 1, we go left, then we go right, and then we process 1, we put 1 into the result array, then we finish 1, then we return to 4, we go right of 4, we see 5, we go left of 5, we go right of 5, and then we process 5. We put 5 into the result array, and then we finish 5. We return to 4, then we process 4, we put 4 into the result array, then we finish 4, then we return to 6. We go right of 6, then we see 8. We go left of 8, we see nothing, we go right of 8. We see 10, we go left of 10, nothing, we go right of 10, nothing. Then we process 10, we put 10 into the result array, then we finish 10, then we return to 8, then we process 8, we put 8 into the result array, then we finish 8. Then we return to 6, then we process 6, we put 6 into the result array, and then we're done. And our order of node visitation look like this. 1, 2, 3. If we look at the implementation of PostOrder traversal looks very familiar compared to the two previous traversal. The only difference is the two recursive calls is now on the top. And if we run our method, PostOrder is gonna give us 154, 10A6. Next, let's do a quick summary for our traversals. This is a simple comparison table. PreOrder, we push first before the left and right recursive call. InOrder, we push in the middle of the left and right recursive call. InOrder also happen to be visiting the nodes from minimum to maximum order. PostOrder, we push after the left and right recursive calls. So this is the summary of our traversals. Now if you might notice that we have 3 lines of code, but if we mix it up a little bit, we actually have 6 possible arrangements. What if we put right recursive call before the left recursive call? If we do this, it's gonna give us 3 more node visitation order. Let's call it reversed order. Then we're gonna have pre-reversed order, in-reversed order, and post-reversed order traversals. Discover them yourselves and see what results they can have. Next, let's do a summary for our tree data structure series. We have covered quite a lot for tree data structure, but in the end we will never forget what we can do and how fast it's gonna be with our data structure. So for tree, binary tree, and unbalanced binary search tree, our insert, delete, and search operations has a worst case scenario of O(n) time complexity. However, our balanced binary search tree or AVL tree or red black tree, we have O log n time complexity for insert, delete, and search operation, and also find minimum and maximum. This is our first data structure that has O log n time complexity for insert, delete, and search at the same time. This is quite an improvement compared to the previous data structures. Next, let's summarize how we extract useful information out of our input. These are the algorithms that we have learned so far. So we have our tree, and tree have the relationship between nodes, our common input for now a tree data structure, our typical problems, and how we solve them is we need to visit the nodes in a particular order, and the equivalent computer programming is we're gonna use loop or recursion to visit all the nodes. Then we use stack or queue or change the position of the recursive call to control the order of node visitation. And in this picture, we have a summary of the order of node visitation with different methods: while loop and queue data structure, visit node layer by layers, the closest layer first, while loop and stack data structure, visit node from root to leaf first, one path at a time, recursion with PreOrder, 1, 2, 3, and 4, recursion with InOrder, 1, and 2, recursion with PostOrder, 1, 2, and 3. You might think that in reality, the order of node visitation for a particular problem might not fall into one of these categories. So what we gonna do when it happens? Well, the answer is simple. You already have a base, this kind of knowledge. Then you can logically add your modifications by using multiple stack, queue, or combination of both. or changing the position of the recursive calls to produce the correct order of node visitation for your problem. There is really a limited set of these kind of problems if you can understand and use these techniques. Combining though with practicing more problems, you will become comfortable solving any problem related to tree data structure. This will conclude our tree data structure series and also our tutorial today. Thank you for watching, and I will see you in the next video.